This week we will turn our view to the last crucial missing piece, and that is how to handle failure in actor systems. This model was inspired by Erlang, and it is centered around the concept of supervision. So when you have a failure, it is contained and delegated to a supervisor, which is then supposed to handle it. This gives rise to the question of how an actor's state is supposed to be handled, which will lead us to the error kernel pattern, and we will also talk about how to persist an actor such that its state survives a failure.
So far we have looked at actors which do exactly as they are told and nothing unforeseen happens. But we need to concern ourselves also with handling the cases which we did not foresee, and that is what we will do in the following. In an asynchronous system which is completely based on asynchronous message passing, there is the problem where failure should go. Normally when you call a method, an exception is thrown and the caller gets this exception and then also is obliged to handle it. When you send a message to an actor, that actor processes the message long after the calling context is gone. The sender has gone on to something else. So where should failure go? In the actor model, there's just one way to communicate, and that is by way of messages, which means that failure also needs to be sent as a message. We take the exception which was thrown inside the actor, we reify it as a message, and we send it, well, to whom? One possibility would be to send it back to that actor which had sent the message during whose processing we just failed. Let's step back a bit and try to visualize what that means. Let's say you're standing in front of a vending machine and you put in the coins and you select your product, which means you make a request to the machine. And then something goes wrong. The machine is not in a state where it can sell you things. And then you get to handle the exception. That basically means that the customer of the vending machine, you, is responsible for fixing it. With actors, we can do much better than this. The inspiration for how actors collaborate is taken from how we humans work together. Just like we form teams, actors work in systems. And the failure of an individual is handled by the team leader or, in that case, by another actor. In our society, we apply this pattern in a hierarchical fashion. Let's look at, for example, a big corporation. This big corporation might be divided into different divisions. For example, marketing, sales, and engineering. And engineering, for example, might have different product teams. And within the storage group, for example, we might have the file systems and the database. All of these teams on all levels have multiple members and one leader. The leader of the whole corporation is, for example, the CEO. And in the database team, it might be the project leader for the database. Let's say that in this team, someone falls sick. Now the leader has to either redistribute the work among the remaining members of the team or ask for help and additional resources. If he cannot fix the problem himself, he will therefore have to escalate it to his boss. The boss of the storage group might then decide either to pull in resources from file systems, or if they are underwater as well, she might just escalate it to the leader of the engineering department. And this goes on until the top, making sure that every failure is eventually handled. This is precisely how actor systems do it as well. Resilience means recovering from a deformation, so to get back to the proper shape and form and function that it used to have before something went wrong. In order to achieve this, we need two things. First of all, containment, which means that a failure is isolated such that it cannot spread to other components. The actor model naturally takes care of this because we have seen that actors are fully encapsulated objects. The second is that failure cannot be handled by the failed component because it is presumably compromised, so the handling of failure must be delegated to another. For actors, this means that one other actor needs to decide what to do with a failed actor, whether it shall be terminated or restarted. Of course, it would be confusing if this decision would somehow be taken by more than one actor, because they would have to collaborate. So in practice, it needs to be done by exactly one. And this means that if you look at supervision, there is a hierarchy which is formed. So if you have one actor here, let's call it top, which supervises 3 other actors, A, B, and C. It will handle all their failures, and in order to do that, it must also be able to restart them, or when it terminates them, to recreate them, to get the service up and running again. This means that top is not only the supervisor of A, B, and C, but also its parent. The 2 hierarchies which are formed, the supervision hierarchy and the creation hierarchy, are the same. In Akka we call this mandatory parental supervision. How does this supervision hierarchy reflect in code? Let us look at one example. This class called manager is an actor which supervises 2 children. It creates a DB actor and it creates an important service actor. Let's call them DB and service. This manager must declare what shall happen in case of failure. We say override val supervisor strategy to override the default. The default would restart all children when they fail. We want to do something else here. So we say we have a 1-for-1 strategy. I'll cover variants in a second. And then we give it what we call a decider. This is a partial function here with 3 cases. In case we have a DB exception from the DB actor, then we restart it. This will probably tell the DB actor to re-establish the connection to the database in hope that the failure was transient and will be fixed by reconnecting. The second case describes what shall happen when the actor receives a kill message. You can write actor bang kill, which is a case object, and this is handled automatically by the actor context, and which will make the actor throw an exception, namely this actor killed exception, and then the supervisor gets to decide what to do, and usually the intention was to stop the actor, so that's what we do here. But what if this very important service actor fails? This manager depends on it. It cannot function without it. So it cannot fix the problem itself. Hence, it escalates this exception to its own supervisor. We have started from the premise that failure is communicated as a message, just as anything else between actors. Hence, it also acts like a message. It is sent and processed like a message. This means that the supervisor strategy declared inside the actor has full access to the actor's state, just as any message processing would have. Processing failure messages is sequentially serialized with all other messages as well. They go through the same mailbox, which means that no normal message can be processed while a failure is currently being handled. In this example, we use this power to implement a bit more refined scheme. First, we create a map restarts from actor ref to integers, which defaults to 0 for the values. Then, when we get a DB exception, we actually look in the restarts map for the sender of this failure and check. If it has failed too many times, then we remove this actor from the map and stop it. Otherwise, we update the map, increasing the failure count for this actor and issue a restart. This is just a very simple example to make it fit on one slide. You can do any kind of processing you would like. It is important to note that this should be a value and not a def. It would also work if you write overwrite def, but then this strategy would be reinstantiated during the handling of each failure. And that is usually not what you want, and it is not particularly efficient. There are variations on what you can apply. For example, the one-for-one strategy always deals with each child actor in isolation. If a decision shall apply to all children, then there is also the all-for-one strategy, which means that the supervisor is supervising a group of actors which need to live and die together. Let me show you an example of this. We have a supervisor here who is just super, with 3 children, A, B, and C. Now, if A fails, so it will send the failure, the supervisor gets to decide what to do. And if it will restart A, then all of them will restart. If A would have been stopped, all 3 would have been stopped together. Both the one-for-one strategy and the all-for-one strategy can be configured to include a simple rate trigger. This means you can tell it to only allow a finite number of restarts. Here is an example. One-for-one strategy allows the specification of more arguments. This max number of restarts, 10, means that after 10 restarts, a restart would turn into a stop. The other feature, which is demonstrated here as well, is that this can be applied within a time window. So if there come 10 restarts within 1 minute, it's still fine. The 11th in the same minute will be turned into a stop. An actor is restarted in order to recover from failure. The benefit of this is that other actors can continue communicating with the service provided by this actor before and after the restart without having to fix the problem. That was the initial goal. But this requires that the identifier by which other actors refer to this actor must be stable across a restart. In akka, the actor ref stays valid during a restart. It is just the actor object behind it which is swapped out during the restart, as we will soon see. There are other ways to implement that. For example, in Erlang, actors which fail always terminate, and they are replaced by new ones. In order to give them a stable identity, there is a name registry into which the so-called PID is registered. One issue with this approach is that clients of this registry must be able to cope with the fact that a name might be registered at one time, then when the actor fails, there is no name registered, and then once it is restarted, the name refers to a different actor. An actor in akka has a richer life cycle than a PID in Erlang, which is a trade-off between this additional complexity and avoiding the race conditions during restart. So far, we have talked about restarts in an abstract fashion, saying that it fixes the problem. But what does that really mean? Expected error conditions within an actor are typically handled explicitly. The sender will get a failure response, as we have seen in the bank account example. It is the unexpected errors which we are concerned with here. And anything unexpected, so an exception which is thrown which we did not foresee, for example, indicates that some part of the actor's state has become invalid. The decision whether a possible failure is treated as an expected or an unexpected error is one which needs to be taken on a case-by-case basis. But the goal of the actor model is to keep each actor as clean as possible, concerned only with its own business, and have the supervisor handle the rest. As a consequence, the supervisor's action will be coarse-grained. It can only stop, restart, or escalate. In this sense, the only safe action the supervisor can take upon a restart is to cause the actor to install its initial behavior, to return to the initial state, because that supposedly is a valid one. Now, how does an actor's life cycle look like? At first, it will be started. This happens when the parent calls context.actor_off and giving it the props. When the call returns, this start action will be scheduled to run asynchronously. The first thing which happens is that the actor context, the actual machinery, creates a new actor instance. This will run the constructor of the actor class. The second is to run a method, a callback called pre-start. This is executed before the first message is processed. Until this point, messages may have already been buffered in the actor's mailbox. The actor then begins processing messages, and maybe it fails here. The failure reaches the machinery, the actor context, which will then consult the supervisor what to do. Once the verdict comes back, let us say it was a restart. What then happens is that on this actor instance, another hook is called, namely pre-restart. Then this instance is terminated. The object is not referenced any longer. It will collect it by the virtual machine's garbage collector. The next is that a new instance of the actor will be created. Again, a hook is run, this time post restart. No messages will be processed between the failure and here. The message which caused the failure will not be processed again, because presumably it could also have been the cause of the failure. Then after post restart, the actor resumes its actions. After a while, let us say the actor wants to stop. It signals this to the actor context, which will initiate the stop procedure. As part of this, the last hook will be run, called post stop, and then the actor instance will be terminated. Restarts, so all of this can happen 0, 1, or any number of times, but an actor will always have one start event and one stop. And after the stop, it is completely terminated and cannot be restarted anymore. And it should be noted that at this place, this is where the actor's state is cleared out because it was supposedly invalid and replaced by a new one. No internal actor state can cross this red line. The actor lifecycle is reflected in source code by the actor lifecycle hooks. Here we have the pre-start method, which does not get an argument. Pre-restart, we know the reason by which the restart was caused, and we may know the message. which was processed while the actor failed. The default behavior is to stop all children at this point, because child actors are considered part of an actor's state. Then, by default, the post-stop hook is invoked. After a restart, post-restart again is invoked with the reason, and this defaults to pre-start. And the post-stop hook is the one which will be called after the instance is no longer running anymore. Let me illustrate two different ways to use these hooks on two examples. The first one is an actor representing a database connection. This DB actor, in its constructor, calls DB open connection to return a handle to a database. When the actor is stopped, it needs to close this connection. By default, during a restart, of course, the constructor will rerun after the restart, and before the restart, the handle will have been closed. This means that the actor is fully reinitialized during a restart. Another possibility is an actor which has external state. This listener will register with a source to receive events. In pre-start, it sends to the source a message, register listener self, which means it registers its actor ref to receive the notifications which it desires. As we have seen, the actor ref stays valid over a restart. So, pre-restart, we do nothing. And post-restart, there is no reason to re-register because we did not unregister. Only in post-stop do we send to the source the unregistration command. It is important to note that actor local state cannot be kept across the restarts. Remember the red line. Only external state, like this registration, can be managed in this fashion. You will also have noticed that by overriding pre-restart to do nothing, we also do not stop child actors upon a restart. In this case, the actor context will recursively restart the child actors which were not stopped.